plus I square root 3 over 2, and then gamma 2 equal to minus half, plus and minus over 3. And these two root give us two basic functions is e minus t cosine 3 over 2, and then in the solution we got e minus 2t, this t, produce cosine sine. One is cosine, one is sine, square root 3 over 2t. So these two roots give us these two functions. And these two functions, we have all real. This real part become exponential minus half t. This item, this the item gives us cosine and sine. So the item gives us cosine and sine. The item gives us cosine and sine. The same thing here. Okay. So the real part of eigenvalue of the root gamma 1 provide us exponential minus half t. The imaginary part of square root 3 over 2 give us the cosine and sine. Now we have to note that the roots gamma 1 and gamma 2, they always come as a pair. In other words, if you have plus I, you also have a minus I. So gamma 2 is always the conjugate of gamma 1. They both come with a pair. You cannot come alone because the real system don't have the complex response. Have you heard about complex response, dynamic response? No. Always real dynamic response. If you want to have a real dynamic response, your roots must have the complex and complex conjugate, because the imaginary part will be eliminated when you write in terms of cosine and sine. Okay, so if you look at carefully this term, e term, this e term give us, let me change to red one. This e term, this is our, we call the damping term. This is called, we call damping term. And this cosine and sine, this is oscillating . All right. In other words, if I don't have the e term, I have only cosine and sine, that's just a spring. They will oscillate for good, forever. They won't stop. If I have only e term, not cosine and sine, in other words, I have only real part, no imaginary part, then I have no oscillation at all. I have no spring. So if you have the e term and cosine and sine, means I have the combination of the damping and oscillations. All right? This is the physics. So later on in the control design, you gotta make sure that you have some, if you wanna have some damping, you gotta make sure that you have a negative real part of your roots. All right? For your controller design. So, if you have a good controller design means that if I don't want the system oscillating all the time or for good forever, then I have to design a system such that the roots have the negative real part. Understand now? Well, to solve the math is easy, but to understand the solutions, that's how we learn how to design the controller. So, look at this. If you look at this chart, then you will be able to see that, see, this is coming down, and then coming up, and down, and then almost gone. The same thing here, you're going up, and then coming down, and going down. See? That's the complex roots. So we learn the real roots, we learn the complex roots, and in all the dynamic system, most of the system are the complex roots. For example, this building, when it becomes oscillating, when we have strong wind, we have typhoon come in, or we have earthquake come in, that it should have like this. If you don't have like this, then I suggest you run away quickly. All right. So you get this. There's no building designed such that without a real root path, without E, that won't exist, because that's too dangerous. Okay, now let us look at repeated roots. Repeated roots, you gotta be careful now. There are some systems can repeat repeated roots. Now give me a system which has repeated roots. Which one? You already done it. I taught you one. Oh, forget about it. I just taught you last week. The rigid body motion has repeated roots, right? Both are not zero. Agree? So in real system, you do have repeated roots. Now, what is the characteristics of repeat roots? Now, assume we have gamma 1 equal to -1, gamma 2 also is equal to -1, then what happens? The solution, what is the solution of this? It has a general solution of C1. Now we are talking about homogeneous solution. We are not talking about any force function yet, not yet, all right? So its general solution is y C1 equal to y equal to C1 exponential minus t plus C2 t exponential minus t. So we have a t involved here. All right, when t going to very large number, 1,000, 10,000, and what happened? Unfortunately, we have exponential minus t here. Hopefully, this one will reduce that t growing. If you don't have this e to minus t, then this t is going to infinity. All right, that's repeated roots. The e minus t, look at this, because there's no cosine, there's no sine. Then what happened? It's going down, shoot, down. Right? Now, the next term, you have e minus t, but you are not cosine and sine, but you got a t in front of e minus t. Fortunately, that's e minus t, that's minus t, 1t. That's 1t is enough, because it's going to grow when t is small. When t becomes very large, it's going to coming down, because even T is growing, E minus T is decaying. The speed of decaying is faster than the speed of growing. So that's what it is, curve come out. Now this is important because your rigid body motion will look like this. In matter of fact, your rigid body motion is growing all the way. Right? Your displacement can go forever. If you have initial velocity or initial displacement, it's going, keep going. It won't stop. So I'm talking about how you see the physics of all these kind of solutions. We have more. Repeated complex roots. What's going to happen like this? This now we have repeated. If we have a force power, then you have repeated complex roots. Is this good or bad? Do we have a system like this? All right? A solution like this. That's the solution. If you have repeated complex root like this, I say repeated. If not repeated, you have no problem. But repeated, you got some problem. Because this solution, if you are not careful, it's not stable.